in this case. Are you alright with that? That should be equal to, now I go to this guy here. If our direction is to my right, this is going to my right as well. So what is the momentum of that one then? mb times what? What is momentum? That is times velocity. What's the mass of that? mb. What's the velocity of that? v. That is positive because it is going to my right, my before direction. So also plus this guy I do not know. So let's say that the velocity is going to my right as well. So m, you don't have to really worry about the velocity direction. Just take an arbitrary direction. Okay. Let's say I took it to this. So it is v prime. That's what I'm doing. So that comes in as part of as well in this. Now what can I say? I'm trying to find v prime. So I'm going to isolate this term. So this will be, I'm going to take this guy to the other side and I get mb. So to isolate v prime, I have to divide both sides by m. So I get v prime is equal to negative mb divided by m times. What does this tell you? If you are given this velocity that I threw the ball out with 5 meters per second or something, that value goes in here, right? And then what am I getting now? I'm getting a negative value. What does that mean? Actually, although I mark my velocity going to my right, really I'm going. When you toss anything, they have to go opposite ways because earlier your momentum was 0, otherwise they will never be equal. Make sense? So the same thing, let's say an astronaut gets outside the space shuttle and has a range and trying to toss it to another spacewalker. What will happen to the astronaut? Earlier the astronaut and the space and the range was stationary. He or she threw it to somebody, and that person should be. Same thing with a gun. You shoot a bullet, gun shoot. That is what this problem is talking about. You have a archer shoots that an arrow has a mass, has a velocity, so that means the archer and the bow has to be going the opposite. There are 3 types of collisions. At least in my book. Book doesn't really word it exactly the way I write it. I word it, but I think my definitions are little more less confusing than the books. The way I classify my collisions are: one is perfectly elastic, which you have an idea from the last lab. What's the meaning of perfectly elastic? You did this experiment in the lab. What was that all about? Which lab was that? You did 2 labs last time, right?
With like the different
the centrifugal force.
Coefficient of restitution experiment. Okay, you had a ball, you let it drop, it bounced back. It hit the bottom steel plate and bounced back. Okay, so that is a collision. Okay, and in that I mentioned that if it is perfectly elastic, what should happen to that object? It should bounce back to the original level where it got dropped off, right? And I said in real world it never happens. Why is it? Some of the energy is lost in the collision. Okay, why is it lost? But the molecules are getting, the object is getting deformed. You saw the video of that golf ball. You can see the molecules have to cross all the way to the opposite and come back. So you can imagine how much energy is lost, because when molecules rub against each other and travel, a lot of energy is lost because of the okay. a lot of energy was lost due to that collision because the body got deformed. It was a round body. When it hits it, you can see it becomes kind of a horizontal. If not, it can even go the other way. Okay. And then a lot of energy got lost, so it cannot bounce back to the earth. It depends on the material how much energy will get lost. You observe that in the lab, right? Some got like the that marble that you dropped almost bounced back to the original height, but not quite. That was the highest that bounced back, I thought, right? The marble. And then the lead did not bounce back at all. It's just all the energy went to deform that piece of lead. If it was perfectly elastic, it would bounce back to its original height. That means there's no energy lost, okay? Which is impossible. So the types of collisions is one is perfectly elastic. So what is the condition for perfectly elastic? What happens in perfectly elastic collision? No energy is lost, right? That means what? Whatever the energy before collision should be equal to after collision. And keep in mind, no matter what kind of collision event that happens, whether it's perfectly elastic or not, momentum is conserved. It has nothing to do with elasticity. Okay? As long as two objects are hitting each other without an external force, momentum is decreasing. Yep.
Is this a form of potential energy?
No, because most of these collisions we are talking about is on a horizontal plane. The two cars coming and hitting each other, but remember, when the cars are coming and hitting, engines have to be turned off. If the engine is on, then there's an external force acting on that, right? These are just two cars rolling, either on neutral, they come and hit each other, then bounce back, or tangled up, or whatever. So most of these energies that we are talking about is kinetic. Question.
So can you just repeat what you said? The momentum is conserved when it
Doesn't matter whether it's perfectly elastic or not. I mean, momentum is always conserved. That's a given. As long as it's a collision, momentum is conserved. But this is a special case when it's perfectly elastic on top of momentum being conserved, energy is conserved as well. Perfectly elastic. So two things, momentum, that means T, conserved, and then E, conserved. Energy conserved. That means total energy, actually it is potential plus whatever the total energy is, but most of the collisions that we are talking about will be on a horizontal plane, so we are talking about 20 kilometers. Okay. Then the other one is perfectly inelastic. Book doesn't use this word perfectly in front. What does that mean? Perfectly inelastic. Can somebody give me an example of a perfectly inelastic collision? It's the opposite to the perfectly elastic. Perfectly elastic bounces back to the original height. So what should happen to this?
Is it that it doesn't move from where it hits?
You did that experiment last time, right?
Yeah, with like the lead ball.
Lead ball. It never bounced back at all. Okay? It stays, it got, quote unquote stuck to the plate, so to speak, right? Or else you take some gooey ball and hit it against a wall or something. Take mud and don't do that at home. But if you were to think about taking a mud ball and then throw it someplace and it sticks to that wall or whatever, okay, that's a perfectly inelastic collision. That means two objects that are hitting each other sticks together. Okay, sticks to each other. Doesn't mean it has to be stationary, but both can stick and then move together as one. Okay, that's the meaning. So it's perfectly inelastic. what is conserved in here? Only momentum, because this is the most energy lost. Like in the case of the lead ball, we know all the energy got lost in that, right? So this is the most energy lost is in elastic collision. And the next one is, that is the most, I wrote it as a 3. This is the most common that happens in real life. That is, I call it elastic. That is in between perfectly elastic and perfectly inelastic. That means it bounces back to some height, but not to the original. It doesn't stay at the bottom. Okay, bounces back to some height. So this is the most realistic in life. I call it elastic. But the problem is that when the book calls it elastic, they mean perfectly inelastic. Perfectly elastic. But I use the words perfectly in front to distinguish that from something bounces back in between, not going to the very top. You understand my terminology now? Perfectly elastic means bounces back to the original height. Elastic means bounces back not to the original height, but somewhere, it bounces back. Okay? Perfectly elastic means it doesn't bounce back. They stick. Okay? So in an exam, I will give you perfectly elastic, perfectly elastic. If I just say it is elastic, that means it's either it bounces back. So in these two cases, only P is considered. Okay, so those are the types of collisions. This one here talks about perfectly elastic collisions, but in some of the problems they don't talk about perfectly. They just say it's elastic, supposed to interpret as perfectly elastic. And the hard thing about elastic collisions is perfectly elastic collisions is on top of the momentum conserved, you can write the energy conserved too. So the algebra gets little heavy. Okay? Because you have 1/2 mv squared. Squared terms are equal. So to solve for one gets little difficult. So I probably will not. I might, if I give you, I'll give enough data for you, all the numbers except for one, so that we can simplify it for that. Strictly speaking, you don't have to be given all 3. You know what I mean? What I mean by 3 is what is the initial velocities and one velocity of the after collision. Strictly speaking, for perfectly elastic, you can calculate what are the after collision, what are the velocities. Because you have 2 equations, you can use 2 and so on. But that's a little difficult question. Algebra wise, it is a little difficult for lots of students. Alright, the next one is, I'm going to go through these couple of sections that are left and then we'll work out some problems. Glancing collisions. Up to now we talked about head-on collisions. That means, what's the meaning of a head-on collision? How do you interpret a head-on collision?
Both objects kind of stop because they collide.
They're on the same path.
They are in the what?
Like they're in the same lane, you could say.
Yeah, the centers of the 2 objects are on a straight line. Okay, that's straight. The centers of the 2 objects are on a straight line. Meaning of that is this guy and this guy. They don't have to be the same size, but centers are the same as of the direction of velocity. This moves this way, this moves this way. That's a head-on collision. Once they hit, they can bounce back, they can stick together. It all depends on what type of collision it is. Then the glancing is, it is little off. You know what I mean? They are not at this. So this goes like this and hits that top part, and then this ball is going to go in. Like when you're playing pool.
Mhm.
You want to cut a ball to the pocket, so what you have to do is to hit that on the side so that if you have head on, then it's going to go straight to the edge and bounce back, unless that's what you want to do. So this is what's the definition of a glancing collision. So this will come in and then hit here. So this is going to go like that. The ball, cue ball is going to go in an angle direction somewhere. So that's a glancing collision. Now the problem with glancing collision is two-dimensional. If you look at it, before it hits, it's one dimension. After it hits what? This will have a velocity in this direction. Cue ball will have a direction in this direction. So that's neither in the direction of the original motion or perpendicular to that. What you have to do in that case? Components. Resolve the velocities of each of those in the direction, in the x, quote unquote, x direction and the y direction. Just like other two-dimensional motions out here, like the projector. That's what I said. It's very important to get the components, you know what I mean, how to resolve the components and use a preferred direction. That's all about this vector equations. Now let's take a quick look. There are a couple of types of glancing collisions. This one here at the bottom of this page here. This is a glancing collision as well. This is an accident that is happening at an intersection, and so these two cars are not coming head on. You know, one car is going, let's say, north, the other one is going east, and they hit at that intersection, and then they get tangled up. After hitting, you know, then it becomes tangled up. What kind of collision is that? Perfectly inelastic, you know what I mean? That's the meaning of perfectly. Okay? So, if two objects come together, after the collision, you have only one composite object. Okay? Those two objects became one big object. That's the meaning of perfectly inelastic. It's the same thing as of, you know what I mean, something sticking to a wall, sticking to something else. So, the two objects that are hitting each other become one. So, this is perfectly inelastic collision. Let's see how we can handle that kind of situation.
Yeah, I was wondering why your erasable markers aren't erasing.
I mean, I'm using, that's what I checked to see whether I'm using the wrong kind, but it is erasable, but it doesn't erase. I use water to erase it.
I have to bring some of mine.
Alright, I'm going to make up a problem that is in the same spirit as the one that is given here. Let's say that one object is going to my right. Let's say this is a 1000 kg object, and going to my right with 20 meters per second. And then the other object is going in this direction. Let's say it is going north, this is going east. This is going with 25 meters per second, and this is 2000 feet. Everybody understand what's going on? One object is going east, That is 1000 kg mass going east at 20 meters per second. The other object is going north, let's say, at 25 meters per second. That is 2000 kg. Now they get into a collision at the intersection. They get tangled up. So what kind of collision is this?
I said the same thing.
Perfectly
Inelastic.
exactly as of okay. So this is before. Now after, how would I write after? I have one big mass here, right? Both of them combined together. So what is that mass? 3000 kg. Okay. And what is the velocity of that one? Some angle is going at an angle. Okay. I do not know. Now the question is, what is this velocity? That means the magnitude and after that. So this is before, this is. And we know these are collision problems. Okay. That means what? Momentum is conserved. Okay. Whatever is before should be equal to after. But only problem with that is this is going at an angle. I have to use a preferred direction, right? What I would like to use is either in the x direction or y direction or east or north or whatever, however you put the direction. But this guy is the spoiler here, right? That means what? What do I have to do? I have to get a compound in that direction and compound in this way. Okay. So what would that be? This component would be what? V cosine theta. What would be this component? V sine. Why did I do that? Because I have velocity going in this direction and this direction. I want to repeat the same thing after. Now this guy.
So it's 3,000 kilograms, they both come together since it's perfectly inelastic.
Exactly. They moved up together and then move. The whole wreck moves in some velocity at some direction. That's what it is. The way that will be worded in a test, if I were to give something like that, would be they tangled up and then move as one object. All right. Now I know momentum before is equal to momentum after. So let's first write it. Momentum before is equal to momentum after. Now what's my preferred direction? Remember, I have to use this thing in two directions to find out. There are two unknowns here, right? What are the two unknowns?
The theta.
V and theta.
Mhm.
Okay, I have two unknowns. That means I have to solve for two. I have to write two equations. So first, let's say that my preferred direction, I'm going to use it in this way. Okay. Momentum before. What is the momentum from this guy in this direction? 0. Remember that? Whatever the y component has 0 contribution in the x direction, whatever the x vectors will have 0 contribution in the y direction. So this one has momentum only in this direction. I'm going to use x and y instead of east and north. Okay, this is my x direction, this is my y direction. So this one has only momentum in the y direction, but I am interested in the x direction. So therefore, contribution by this guy is c. Okay, so only contribution is coming from this guy. What is the mass of that? 2000, right? What's the velocity? 20, but it's positive because my preferred direction is to my right. Say that again? I'm sorry. 1000, that is the mass, and then the velocity is 20, isn't it?
Mm-hmm.
That is positive because my preferred direction and that direction are the same. That's all the momentum I'm getting in the x direction from that before. Okay. That should be equal to what? Now after the wreck, I had to worry about this one only, right? Because the contribution from this is 0 in that direction. So all what I have is a 3000 kg object going at v cosine. That is positive because it's going to my right as well. That is one equation. I'm not home free because I have two unknowns. I cannot solve for each one in one equation. So I have to write another equation. What would that be? Again, momentum before is equal to momentum after. I'm going to do it here.
Did you change the direction?
Exactly. I'm going to change the direction. what would that be? So the 1000 kg doesn't contribute here, right? That is to my in the y direction. I mean that's in the x direction. I'm sorry. This is all in y direction. So this guy has no contribution in the y direction. Okay. Only contribution comes from this guy. How much is that? The mass is 2000. Velocity is 25, but it's in the same direction as of my previous direction. So that 25 comes in as positive. It should be equal to. And what is the after the collision? What is that? 3000, and the component that matters is only V sine theta. So I have two equations and two unknowns I'm trying to solve. Okay. I'm going to do I always simplify things before I multiply out, but if you don't like it, numbers and divide both sides by 3000. So what I have on the left hand is 20. So 20 is equal to 3V cosine theta. Then I have 50 here. So 50 is equal to 3V sine. Those are the two equations. Now, what is the best way to solve for this? What our goal is to find V and theta. Okay? What's the best way to solve? Say that again. Divide the second one by the first one. Okay, why is that? You'll understand that. I divide 50, so let's call this equation 2 here. Call this equation 1. What I'm writing here is 2 divided by 1. Use this. On the left hand side I have 50 over 12. On the right hand side what I have is 3V sine theta
And that ratio is basically your tangent.
Exactly, that's the whole idea. Three V's will cancel out, these zeros will cancel out. On the left hand side I have oh, shit.
I'm gonna bring my markers.
So I had 5 over 3 is equal to tangent.
5 over 2.
So to find theta, I will take inverse, tangent inverse of 5. So whatever that angle is. Now I have the angle, then I can go to either of these equations, plug in that theta value and solve it. Pretty simple. Only thing is you have to be very careful about getting the components right and what direction you are going to use this. That's it. So vector equation, direction is very important, and then to see which ones are positive. Make sense? There will be a question based on some principle like this. Either it could be a totally inelastic problem, or it could be just things bouncing off. Okay, those are the most possible questions that will be on the next test.
When you first started to explain all of this, my initial thought was like that the resultant was actually the equilibrium, because you had two objects kind of connecting right here like this.
No, what you are saying is right. You take the momentum of this, because the momentum is the momentum is the vector quantity. Okay? You take the momentum of this, take the momentum of this, then the resultant momentum is in this place.
Which
you
is
can do that.
Which is the equilibrium.
Okay. Which is the not the equilibrium, but the result.
That's what I was saying. Like my mind was thinking that they're connecting right here and making this angle. That was but that's the resultant.
You can do that. So this, what he's talking about is we have a resultant momentum here. So you have the x component of that momentum and the y component of the momentum. So you
Okay.
multiply this by this, that is your y component of the momentum. Multiply 20 by 1000, that's your x component of the momentum. Then the hypotenuse will give you the magnitude of the momentum. Okay. And then to find the velocity, what you have to do? You divide by the total mass, then that will give you the.
And if we have a resultant vector going in angle theta, would like let's say we had b at theta, would the equal
I'm not
be
to say it.
b at theta minus 180?
Theta minus 180 or theta plus 1.
Okay,
Both are the same.
but it's still b. It's not negative. Okay.
You're going and asking questions about the test.
Hmm?
You're done with it. Okay, let's go to just the book here. Let me pick up an example. I want to talk about this here. Be careful here. A ball is approaching the wall at an angle and then it bounces back at the same angle. So this is called the incident angle. Actually, incident angle is this one here. This is the reflection angle. They are the same in this case because if this angle is theta, this is theta, then left over from the 90 would be this. This will be the left over from the 90. These two angles have to be equal as well. In this case, they ask him for what is the impact on the wall. Impact is phi. What is I equal to? There are two ways you should be able to relate I to. What are the two ways? Delta P, right? Delta P, and then what is the other one? I is equal to average force times delta T. Force times the contact time. Remember?
Yeah.
So I is the same. I can be expressed in two ways. Now to find the impact at this wall, if you look at it, I can resolve this to a vector going in the positive y direction and vector going in the positive x direction. I can resolve this guy to what? Vector going in the positive y direction and vector going in the negative x direction. Okay. What is delta P? Delta P is the momentum after minus momentum before. For the y component, what is the change in momentum? What is the momentum after? Remember, momentum comes from velocity, right? Because all you have to do is to multiply by the mass of the object. It doesn't change here, right? Now, you have a compound in this direction, that is momentum, that is after collision, right? You have a compound in this direction, that is before collision. How can you say about the change in the velocities? There is no change in the velocity, right? Because this one is what? V cosine theta, this one will be V cosine theta. So there is no change in the momentum in the y direction, if you notice. Okay? All the changes in the x direction. What is the change in x direction? What is the component after? After is in the negative x direction, right? What's the component going in? That is in the positive direction. This should be a negative of a minus value because your direction is going to the okay. So there will be whatever the 2 times that component value of that. So be careful about that. There is no impact along the y-axis. It is just bouncing off of that, and all the forces are coming off from on the x-axis. Question.
Would it be the sum of those
Some of those two.
going in that direction?
Yes,
Okay.
going in that. Lot of students think they cancel out. No, because when you
That's
take
what
the
I thought at
direction, you
first,
have a
right.
negative of a minus value. Alright, let's do this. This could be on your homework problem, but let's work it out. They ruined it for me, but that's okay. The whole point here is I was trying to make is once I went to a party at a friend's place, and I never played pool in my life. I'm not a pool player. And all what he had was a pool table. So everyone got together in the basement and started playing pool. That's the first time I ever held a, one of the wand or whatever you call it.
He said a
I don't
wand.
even know the term. All what I knew was I had a white
see.
ball. I had used that to put the other balls in the pocket in some order or whatever. They didn't care about the order in the game because no one really knew much about pool. But I knew my physics. Everyone, when you're trying to cut this ball, what they think is it will go in this direction and the cue ball is going to go equally with an equal angle on the other direction. Okay? But I knew my physics better. I knew that if I cut it like this, my cue ball is going to be 90 degrees to that, the direction of that. So I knew exactly where my cue ball is going to end up. A lot of my other friends cut the ball and then ended up the cue ball going into the pocket. That's a penalty, right? In pool. So they got into penalty after penalty, thinking that the balls are going to go equi-angled on the board. But I knew it's going to be 90 degrees, so I could aim it, and then I won almost every game. All the first and the last game I ever played pool. That's because of this. If you notice that if you add these two angles here, you can see that is 37.53. When you add it, what do you get? 90. Intuitively, you think that this will be 53 as well, but that's not the case. That's the whole bottom line. So in this one, what we have is this ball is coming at 5 meters per second. This ball is stationary. This is the cue ball. This is the target ball. Then this is stationary. So this is before the collision. After the collision, you have this ball going at 53 with some velocity here. And then the other one going at 37 with a velocity. And keep in mind, this is only true, the angles will add up to 90 degrees when the two masses are the same. Okay? That means the cue ball and the target ball have to be about the same mass. Otherwise, the angles are going to be but I think
how would it change the angles if one was
it all depends on the ratio of that.
Okay.
So you can take different masses and then try to calculate.
Okay, it'd be a sharper angle if the
If it is a
stationary
heavier
object.
body, yeah, it will be a sharp. Alright, so now the problem is, now this is nice and good, right? Because it's in the x direction, so to speak. That before. You see that? One guy is stationary, that's even better. Because what is the better thing about stationary object? Momentum is zero, you don't have to worry about that guy, right? So only momentum coming before is from what? The cue ball at 5 meters per second. Understand that? That's in the x direction. But this guy is not so good because it's an angle. Same thing with this guy, it's an angle. So how do we handle those situations? Get the compound in the x direction and the y direction. Get the compound of this in the x direction and the y direction. Okay, that's all we do. Then we have to apply the same principle like as of before. Momentum conservation in the x direction. Okay. Then the momentum. So it will be two compounds. One from here, one from here. So you have VOF and VRF. Okay. So those two will be in the equation. So this will be what? VOF cosine 37. This will be VRF cosine 50. Yeah.
So in this case, would the before collision, when you make your two separate equations be the same? So, like in the example we did on the board, since we had two cars.
Yeah.
Never mind. So when we have two cars over there, so we had to take into account both of them.
Yeah.
So how does it work in this case? I'm still confused.
That's stationary. One stationary. Those were
Okay,
moving.
let's write down the.
Okay.
Let's write down the.
Now I get it.
You get it?
I think so.
Okay. So the first one before would be just 5 times what are the mass of that. You know what I mean? So you get only 1 term. Okay. Then the other guy is stationary. It doesn't contribute. But after would be VOF cosine 37 times the mass of that. Then VRF cosine 53 times the mass of that. That's in the x direction. You're not done yet. Now you have to use it in the y direction as well. What is the momentum before in the y direction? Zero, because then although that object is moving, that is moving in the x direction. It doesn't contribute anything to the y direction. So one ball is stationary, very good. The other one is going in the x direction, so zero momentum before in the y direction. But after collision, this guy will have a y component, this guy will have a y component. So these two will have contributions after collision. But one will be positive, the other guy will be negative. Those two will add up to be zero, right? Because before collision it is zero. Okay. Now you have two unknowns. What are the two unknowns? B over F and B R. Okay. And then two equations you can solve. Make sense? There's another way to do this thing. What they can do is they give the approaching velocity and the masses of the two and give one velocity. This ball will start rolling with some velocity, 3 meters per second over there. Okay. Then you'll be asked to find the angle of this. They'll give the angle and the velocity. Then you're supposed to find the angle of this one and the velocity. Okay. So you find out when you work it out, this will be complementary angles. That if this was 30, this will be 60, and so forth. They'll add up to be 90. And the velocity will come from. Make sense?
I have a question real quick.
Yeah.
So this was 90 degrees,
Yeah.
the difference, or the sum. And then this one, it wasn't, and that's because these objects were moving.
Yes, that is only true for, like glancing collisions, This is not a real glancing collision, it's kind of a perfectly inelastic collision, that's all.
Right.
Glancing collision means they hit each other and they go their own
And
way.
they always
is not the case.
in glancing, they typically go 90 degrees.
Yes, if the masses of the two objects
Are similar.
the same.
Okay.
The last thing I'm going to talk about is the lab that you did last time, that time before. At that time, you really didn't know the concept here, but this is what happened. So you have the bullet. This is coming from the launcher. That is the mass that is coming in, okay, with some velocity. And this cradle or the catcher was stationary. Remember that? Okay, that's what you had before. So the catcher was just hanging there, and you shot that steel, ball into that. So before collision, this is a collision problem because ball gets hit, ball hits the catcher, and this is a collision problem. Okay? So what should come to your mind? Collision problem.
3. This third law. No?
Momentum is conserved. Every collision, the momentum is conserved. Okay? So you have this block here stationary. Only momentum before is from that steel ball that you have. It has some mass and velocity. So the total momentum before is contributed by this guy. Because this is stationary. Then what happens? Those two, the ball got lodged in it, right? Now it's taken off with some velocity. This is after collision. Actually, this is not taking off yet. So what happens is this: you have one block here, and the ball approaches the velocity. This is MB. This is MC. This is before. And then after collision, what happens is both of them. So this is MB is here, MC is here. Now they are going to take off with some velocity. You're given, the velocity that the steel ball had, and then this is 0, so you know the total momentum before. This is after. So after the ball gets lodged in that, it's going to take off. Immediately after, that's what we are interested in. Okay? Not after it's flying off or anything like that. Because this is a collision problem. Just think of it on a table. You have a ball hitting something, what's going to happen to it? Block is going to take off, right? That is exactly what we're talking about. Okay? The collision part is that. Okay? So what can you write here? Momentum is conserved. Okay. Momentum is conserved, that means momentum before is equal to momentum after. What is that good for? You can calculate what will be required. That is a takeoff velocity. Okay. So now this block is going to go with the velocity this v prime. I call it v prime. Going to take off with v. Then what's going to happen? Now this is a pendulum, right? It's going to swing and then come to height. Why would it stop there?
It wouldn't stop it, so that.
No, I mean, it won't go any higher at this point.
It's
Why
momentum.
would it?
It's lost its momentum.
This has, at this level, what does it have now? The ball got lodged in it. What does it have? The block in the ball. Kinetic energy. It's at the lowest position, right?
Yeah.
All what it has is kinetic energy. Now it is climbing up. What is that kinetic energy getting converted to?
Potential.
Potential. At the highest point, what happened to that? All the kinetic energy got converted to potential. There's no more kinetic energy. All got converted. That means what? It cannot go anymore, right? It doesn't have any kinetic energy. So motion has to stop. Because remember, kinetic energy is always associated with what? Motion. So zero kinetic energy means it has to come to a stop. Now it came to a stop, but it has potential energy. That is going to drive it to come back. Okay. So what is that potential energy getting converted now? Part of it is going to get converted to kinetic energy, right? At this location, what does it have? All the potential energy is gone now, right? It all got converted back to
Kinetic.
That's the whole idea of a pendulum swinging back and forth. At the two extremes, it has only potential energy. At the bottom, it has only. We'll be doing that in this 104 if you want to take it. That's the first section they'll talk about in simple harmonic. Alright, so now we use this momentum conservation to find out how fast would this block and the ball will take off. Okay. After that, it is swinging to the highest position and coming back. What kind of concept is involved in here?
Transfer of energy.
Yes, what is that called?
Work.
Yeah, you can say work energy theorem. In more simpler terms, it is conservation of energy. What kind of energies are involved here? Only two types of energies are involved here, right? What are the two types? Gravitational potential energy and kinetic energy. At this point, it has only kinetic energy. At this point, it has only kinetic, potential energy. Anywhere in between, it has what? Some kinetic energy and some potential. Okay. Closer to the bottom, it has more kinetic energy. Closer to the top, it has more potential. Okay. So that's how you analyze to find out this V prime. Once you find the V prime, you can calculate how high it goes, or if you're given the height, you can calculate V prime from that and calculate the velocity. So what is happening tomorrow?
Lab report.
Lab report is due. Okay.
Homework still.
No, I told you because you have a lab report and an exam to study, so I'm not going to quiz you tomorrow. Okay.
No homework.
That's what. Now with this, I'm done with the unit. I mean this chapter. Then I have to do the equilibrium. I can't remember what is on the schedule for tomorrow's lab. What is it? Is it equilibrium? Rotational dynamics.
You said next week, didn't you?
Okay.
Oh, you said next week.
Okay.
You said the next exam will be next week, right? Or a week from now.
Week from now, but probably not Monday because I was hoping to do some stuff in the lab, but this is a totally different field. Fine. There's a good chance that I might not go on the trip, so I'll be here for the review and the final. So I'm pushing one of my junior engineers to go out. I told him I'll write the paper. All he has to do is to be a puppet and I'm trying to coach him and try to convince him that he should go. I hate traveling. All right, let's do this. I can't find the worksheet. I was hoping to do some problems before I go, but it's already 9:34, right? And you are a busy day studying for the test. Okay, I'll let you go early today, and tomorrow we'll meet at the lab. Make sure that you bring the lab report to the class when you come in, okay?